Alright, time for another draftphysics.com. Debatephysics.com also, but just can't find an appropriate challenger or whatever you want to call it. Whatever you call somebody who opposes you, somebody to fight with, who can take the heat of the kitchen, so to speak, without getting too hysterical, wetting their panties and whatnot. Anyway. So this old Professor Lewin simple experiment's been done by lots of people, classic physics experiment, and it really does pose the problem if you just do the experiment a little bit differently. And so in this pursuit, the problem is that yes, it's more complicated than one would imagine. Okay, at least I didn't imagine it being all that complicated to actually extract the energy of something. You're just saying, well, there's got to be some perfect way to measure energy, but the problem is that I'm right about the, work equals force times time, not whatever distance is, and yeah, time matters. How long you're applying a force. So I was thinking of the bicycle wheel. Somebody will go to that first, and then we'll describe. Well, let's do that first. Just since I mentioned it, we might as well just do it. So I was thinking about the wheel thing. I do have a bicycle wheel, so it's not like I can't do a bicycle wheel experiment. So I can. So I was thinking of different ways of doing it. And I did realize there is a flaw in what I thought was a simple enough idea. All right, is that you would just lift a mass, so you'd have a little stick and then it would just lift a mass. All right, and then slide off and drop it. So the mass would be on its own little plunger here. The mass would lift up, and the mass would fall down. And then I ran into the same gravity problem where if I lift the mass slowly, it's going to be more work than if I lift it fast. So obviously when it's lifting it fast, it's going to be a lot less work than when it lifts it the distance slowly, because it's more time in the gravity. So it actually won't work. So it seems nice and simple, but no, failure again. So it's just not as simple as everyone would like it to be to do this measuring thing. So I thought of that also, and just the idea of having something bend. And the fact is the slower you bend it, well, the more time the force is being applied to the object. So the longer it takes to go through the bending process, it's the same problem. The longer it takes, the more constant force you're applying to a surface, and so it just adds up to being more work to bend something slowly than to bend something quickly. So again, in trouble. Doesn't work. Yeah, that's a simple statement. So if the times are very short, the difference in the time, well, then it's not going to matter much. But if the time is significant difference, it's going to matter a lot. All right. So that brings us back to this Professor Lewin thing. So I'm trying to think of some way, so here we have the classic experiment, really. We're going to have the 5-ton train going 10 miles an hour going one way, and we're going to have the 10-ton train going 5 miles an hour the other way. And everybody agrees that's what's going to happen. So the momentums will be the same, but the kinetic energies will be different. The lighter object is going to have twice the kinetic energy that this heavy one is. So Newton's third law, not so much. It ain't looking too good, right? So let's zoom ahead a little.
Okay, there we go.
All right, and so there's not, it's not like it's all that much to see here, but we might as well play it through, right? You can see that, right? Yeah. All right, and so what's going to happen is half the energy is going one way, half the energy is going the other way, half the momentum anyway. But the absolute truth is that it's twice as much kinetic energy is going to be going one way as momentum. So visually you can see this. So there's no doubt about it. It's not like it's a debatable subject. I think this should work. Worked before. There we go. So the wire is burnt and the carts separate. And one is going twice as fast as the other. You can see the little carts moving a lot more distance per frame. So twice the velocity one way, half the velocity the other way, twice the mass one way, and that equals twice the kinetic energy. So let's just draw it, and then I'll just make my argument that this sort of proves the point, I think. I mean, this is like the Newton's cradle argument with the 150, increasing the momentum, the 0.75 velocity thing. It doesn't work. You can't create more momentum in a direction and say that's reasonable physics. Why this camera is not doing what it's supposed to do. Okay. Anyway, all right. So we have the experiment. We have what we want. We have the 5 mass going 10, and we have the 10 mass going 5. All right. And so we know there's twice the kinetic energy here. All right. And it was supposed to be an equal explosion. So if Newton's third law meant anything to you people, you would recognize that it has to be equal and opposite. All right. But it's not. We have twice as much kinetic energy over here. So first we have to explain how we can have twice as much kinetic energy, and then talk about equal and opposite reactions, because obviously it's not equal and opposite. Now the momentum is equal. All right, now let's say we put this in a closed container. So now we're playing by their rules, a system. All right, now we've got a problem, don't we? I mean, theoretical problem. So let's say we put a spring on this side, and we put a spring on this side, and they were, very perfect. And so we retain our velocities. They come back together. What are they going to do? Well, they're just going to recreate the same compression in the spring, right? So the spring is just going to recompress to exactly what it was when it initialized. So I'm going to have the same conditions, and if we could get rid of all the friction, this would be an oscillator, and it would just continue to oscillate, right? Now the problem is, obviously, is what's happening if I take away these springs and I allow there to be Velcro here, okay, and so now we're just going to absorb the energy. Now what's going to happen? Well, the 10 mass only has half the energy of the 5 mass, so obviously the whole box is going to move this way. So we took a condition that didn't have any motion in it, all right, and now we have motion in this direction. So that's like violating the rules, right? That's motion from nowhere. We have an equal amount in the explosion, this way and that way. It can't be unequal. It can't create unequal energy. The explosive, the spring, cannot create unequal energy. So how did I end up with unequal energy sticking and moving the box? This can't be accounted for. There's no theory for this. No theory. NT. No theory. This isn't supposed to happen. I can't make energy from nothing. And energy is really just a differential in pressure. Let's understand. We call something zero energy when there's plenty of energy. So any circumstance where you're getting pushed equally from both sides is zero energy. But obviously that zero force can be applying a lot of force. But anyway, so the real dilemma is if this experiment was done on a looped track, and the two things went up and then they came back down and collided, you'd have to concede that they just keep going back the same way they went, and they're just going to keep doing the same thing over and over again, because there really is equal energy, mv over here, that there is over here, and it's momentum that is the definition of its energy. There is an equal amount of energy in this system. There isn't an unequal amount. And the kinetic energy is just a fable, and the box won't do this. This won't happen. So you don't need a theory, because guess what? It doesn't happen. This box will not move in this direction because this kinetic energy is a fake. It's not a real thing. This 2x is not a real thing. It doesn't have any power. It can't move anything. So if I did this in space, all right, simple experiment, right? You just make a box with, two sides. You have an explosion. The two things fly off. They hit the sides and stick, and the box doesn't go anywhere. I mean, maybe this one will hit first because, we have to have the distances based on the velocity. This one's going to take a longer time to hit the wall over here than this one's going to take. So obviously it'll go this way first, right? And then when the other side hits, okay, then it's going to stop, go back to 0. So I guess it could move this way, and then it stops, right? Yeah, so I have to make this side of the box shorter and this side of the box longer, or else you're going to get motion in a direction. So even that's an interesting statement then, right? Because I will get some motion in this direction if this side hits first. Just trying to figure that out, right? And if the box starts moving this way, well, then this side's going to get here closer, but it still can only be, you can only cut that in half. It's still a differential, right? That is curious, right? I hadn't thought of it ahead of time, but it is a curious fact that it's going to gain some motion this way, and then all that motion will be converted into nothing again once this side hits. So there's no way to undo that. You know, except just extend the different distance between the sides. So if I made this one, if I made this distance even further, right, well, I don't want the 10 distance further. That was a big fat mistake there. Okay, I want it closer. I have to make the surface closer over here. Okay, to equalize the two. But I could extend this even further, so I can either do it either way, right? I could make this surface further away, or I could make that surface, okay? And if I made this one extra far away, then this side would hit first. It would have to move in that direction, and this can only stop it. It can't make it go back to where it was. So yeah, so that cheat, you can go either way. You could make it go in either direction by just changing where you put the impact point. So that artifact is irrelevant. I mean, obviously I could make one side open and then only one side hits, and it's going to move in the direction that the one side hit, obviously, because I haven't collected the other side in the same time. So if I don't collect the energy at the same time, I'm obviously not going to not move the box at all. So it's sort of irrelevant to the real major point, which is if I do accommodate the fact that this one needs more distance, twice the distance. Yes, this is only twice the velocity. In space, there's no friction, so it's not going to go 4 times the distance. All right. And so I just make this twice the distance, and I put this back where it was. Then they hit at the same time, and the box goes nowhere. 0 velocity. I think everybody knows that's what's going to happen. I think they know there's a pretty good probability that's going to happen. Okay, so this should be kind of a doable experiment, right? You could put a whole box on wheels, okay, and then you could do the experiment and see if you can make the box move, keep moving when they hit at the same time. And if the box doesn't move, then I'm right. If the box does move, then you're right, right? That if there's more kinetic energy going this way. But I think you know there's no... The kinetic energy isn't real energy, because if I did this in space, it's not going anywhere. Okay, if these two things hit the surface at the same time, all right, so they're going to impose their energy onto the box at exactly the same time, the box isn't going anywhere. And it's a decisive proof that there's just momentum. There isn't any kinetic energy. It's not real. Kinetic energy is not real energy. Momentum is the only energy in the universe. All right. So that seems a doable experiment in some way or another. I mean, it's not that complicated. A spring, 2 motional mention. You know, I could make these billiard balls. I could make these anything. You know, and like even 2 of them tied together. You know. You know, and slide them across glass and have them hit something that's connected. You know, you just have a metal bar, or you could just have a piece of wood, or you could just have any cardboard. It doesn't matter. You know, as long as they hit the 2 sides at the same time and this doesn't move, then you know kinetic energy isn't real. Because twice the kinetic energy won't move the box. It doesn't even make any logical sense, right? You know it's going to oscillate. So if I did the spring thing, you know it's just going to keep oscillating. And if it's real efficient, it's going to just keep oscillating. And you know there can't be twice as much energy on this side of the oscillator. It's not possible there's twice as much energy on this side of the oscillator. It's just not possible. All right. That should be enough. Yeah. All right, we'll go with that. I mean, I could talk about going back to the lever experiment, and the fact is that's probably, you know, with the spring, and you launch things from the different locations, and you should be able to get a pretty efficient mechanism. And that's probably the way to go to create another proof. But it seems to me that this proves it. Now, somebody has a counter argument, love to hear it. But if the box doesn't move, right? So we're going to allow the kinetic energy of the 10-ton train to hit the side of the box. At the same time, the kinetic energy of the 5-ton train going twice as fast hits the side of the box. So if we do that, do you people predict that this 5-ton, twice the energy in this direction will actually move the box in this direction? Is that really your contention? And if you concede the box doesn't move, will you concede that the kinetic energy isn't real? If it can't move the box, it can't be real energy, right? Come on. Can't be. All right. So, yeah, I'll call it a video. And work on some other thought experiments and see if some of them can be converted into real experiments and such. Till the next time.